Well, welcome to Science, everybody. Time for a new lab. This new unit, what we're going to get into is really the Sun, Earth, Moon system. How do those three things create all kinds of stuff? It's kind of a hard unit at times, though this lab is one of the easy ones you're going to do through the year because I'm going to help you do almost the whole thing. So what I usually do, I'm going to make this big right here, is when you're coming in the room with this, I ask you to feel this mountain range right here, where India meets Asia, the Himalaya Mountains. So I have you feel this on this globe. This is a relief globe. It's got these little bumps on there to represent the mountains, or Alps, or Appalachians, or Rockies, or whatever it may be. Okay. I say, what do you think on that? Are those about the right size? Like if I were to take this to scale, if I were to blow this up to the size of the Earth, are those mountains about the right size, or are they too big, or are they too small, or what's going on? So that's what we're going to do. Your lab looks like this right here. And I've got another one on paper right here that I'm going to have to use for a little bit of the measuring, but that's all right. We'll get there. So what are we going to do? A raised relief globe or map has physical features bucking up so you can feel them. The question is, how accurate are these? Maybe you should guess right here. What do you think? Are they too big, too small, or just about right? And the globe we're going to use is really this right here. So since I can't give everybody one of these, it's going to be, if I took this and cut a slice out of it, made it that circle on the piece of paper, and that little bit right there is Mount Everest. I don't know why I'm putting it on the screen, you can't see any point, but that would be Mount Everest right there. Is that about right for the size of Mount Everest, or is it too big or is it too small? We're also going to talk about the roundness. How round is the Earth? Is it perfectly spherical, or is it off? So let's do it. The Earth's real shape, not perfectly spherical. It's called, and you might have to pause to type this over there, an oblate spheroid. It's the technical name for it. With its spin like that, pressure pushing out here, force pushing out there. It's a little bit like smushed at the poles. From pole to pole is a shorter distance than a diameter from equator to equator. So take a sphere and just squish it a tiny little bit, and that's what you got. So we're going to do this roundness ratio, which is really just how round is it? Now, if it was perfectly round, the polar diameter and the equatorial diameter would be the same. So if you go and divide those, you would get 1. So a perfectly round thing has a body. Actually, there's the slot right there. We're going to write that. If it was perfectly round, the roundness ratio would be 1. So however far away from 1 it is kind of like how not round is it. So all you got to do, pretty simple math. Take the polar diameter, divide it by the equatorial diameter. I don't think I'm going to do that for you. I'm going to have you guys figure that out. So take that number, divide it by that number, put it in here, round to the nearest thousandth. That means decimal, 1, 2, 3 spots. Even if one of those spots is a 0, so you still do it. Now the relief globe, this is where you would normally grab a ruler and measure here, but you can't. So I'm going to do it for you. For equatorial, nope, I'm sorry, I'm doing polar first. For polar, I think I'm getting 15.0. So you're going to come back up here. 15.0. And then for equatorial going across, I'm getting 15.5. And if you print this, that might be slightly different because I'm using a different scale from a book of the same lab, of a similar lab. Those were in centimeters. It's not really going to matter because if you really are paying attention to labels, when you do kilometers over kilometers or centimeters over centimeters or anything over anything, they cancel. So roundness ratio doesn't have a label. So divide those out, and you got decimal blank, 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 right? So is the Earth a perfect sphere? The answer is going to be no, but use some data in your complete answer. Which of the two is closer to his perfect sphere? Look at that, and you'll find out. And you'll see that the Earth is actually very, very, very close compared to like even a classroom globe. The Earth is really darn close to a perfect sphere. But again, use data in your complete sentence answer, use some of these numbers. So pause, take care of that stuff. Then we'll move on and say, welcome back. Now we're going to talk about smoothness. And we're going to do these ratios. It's going to get a tiny bit confusing if you haven't done a lot of these ratios, but again, I'm going to help you on like almost all of this. So first, let's figure out how tall Mount Everest should be on a raised relief globe. So if they were to make this scale, the way you have a scale model of like a train back there or something. You know, scale models of trains. Matchbox cars are like scale models. If you blew up a matchbox car to the size of the real car, everything should match, right? If you blew up this planet to the size of the real planet, what's the deal with these mountains? How tall should they be? So, how tall Mount Everest should be on a razor leaf globe? Mount Everest actual height. So it's running. It's going to be some cross multiplying using this equation right here, which is a real basic ratio. This isn't really Earth science equation. It's just a ratio for scale. So the actual height of surface features is 8.8 kilometers. That's what I said right there. So that's done. Use Earth's polar diameter from part one for the real Earth diameter, which is 12,756, if I remember. No, use Earth's equatorial diameter. Yeah, 12,756. So 8.8 over, switch to text, 12,756 kilometers. Yeah, equals. Um, how big would it be? We don't know. X over what is the diameter of the globe that we used, and we're going to again use this at 15.5 centimeters. Right, so you'd cross multiply and solve, and that's going to give you your answer. So that's how tall. Yeah, in fact, I think I'm going to have to do it in order to make sense of the rest of this. So you get a little bit of free work. So that means x would be 12,756 x equals whatever 8.8 times 15.5 is. 8.8 times 15.5 is 136.4. And then what you would have to do, if you know your cross multiplying, is divide by 12,756. Sorry. Divide that side, so those cancel. Divide that side by 12,756. And that's equals your answer, divided by 12,756. So I'm getting 0.011. The answer you got for x is how tall Mount Everest should be on the scale. It should be 0.011 centimeters tall. So that's less than, where's my camera? That's less than a millimeter. That's less than one of those little tiny lines. That's a tenth of one of those little tiny lines. So in reality, if you guessed before that these mountains were about right, or if they were too small, turns out you're way wrong. They should only be a tiny, tiny, tiny bit big, which is like strange because you think of people climbing Mount Everest or the whole entire Himalaya mountains. Wow, those are huge. But on the scale of the whole entire planet, given how big the planet is, they're actually not that big of a bump, which is odd to think about, but it is the deal. So what we'll do then is say, on this one right here, the one that's lower on your lap, how wrong is it? So if we measure how tall that is, yeah. So it's 0.3 centimeters tall. So percent error, this used to be a part of our science and we've kind of taken it out. It's basically how wrong you are, which would be uh, 0.3 minus 0.011. That's like the difference from your measured value to the real value divided by the accepted value of 0.011. So I'll just do that for you on the calculator. 0.3 minus 0.011. So we're wrong by 0.289. Divide that by the correct answer of 0.011. And you multiply times 100 as part of that as a percentage thing as well, which means we're off by 2,627%. So those mountains, this mountain right here, is that percent too big? That's what goes right there. So way, 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 way too big. So the last kind of cool thing we'll do for the size thing is What if I took a globe that was this big? How tall would that really be in real life if I were to take this globe and blow it up to the size of the planet? Well, it's 2,600% too big, so you can probably guess it's going to be pretty large. So what I'm going to do is run this equation again. Only now I'm going to look for this, the actual height of surface features, on a globe that's 12,756 kilometers large. When the feature itself is 0.3 centimeters tall on a 15.5 centimeter globe. All right. Why don't I just run this in a calculator rather than you sitting here trying to watch me struggle with writing it out? So it's going to be 12,756 times 0.3 is that number, the 3,000s divided by 15.5, 246.8 kilometers tall. Now, people get killed trying to climb Mount Everest at 8.8 kilometers. If you were to try to climb one that's 246.8 kilometers above sea level, forget about it. It's not going to happen. So that number is actually going to sneak right in this little slot right here, 246.8 kilometers. Look at your SRT on page 14 of the reference tables. I think we're off the chart anyway, so if you want to bust this out, we haven't talked a whole lot about this atmosphere thing yet, but there's all layers of the atmosphere. We have to learn it soon. And if we want to know at the top, well, this thing only goes to 160. So in other words, you're pretty much in outer space. If you were to climb a mountain that tall, you would no longer be in the atmosphere. What layer of the atmosphere? It's not even really a layer, right? You've essentially, like, you're almost like you could almost knock on the door of the space shuttle or the ISS floating around out there. In real life, Mount Everest is only 8.8 kilometers tall. So, along with everything that you've ever done and all of our weather, uh, are all there in the troposphere. We'll worry more about layers of the atmosphere when we get to urology. Okay. So, what object would actually make a good scale model of Earth? This is a terrible scale model. These things are thousands of percent too large. Now, they do that so that we can feel the bumps and all of that. That makes sense. But what would really make a good scale model? Think about it for a second. I'm going to go find one. People sometimes will say golf ball. Those little divots on a golf ball would be, I mean, giant craters. Like the Grand Canyon would be nothing next to them. Sometimes people go, okay, smoother, and they'll go with like something like a lacrosse ball. But even that little ridge right there would be enough to like completely separate, commerce and weather and everything from one side of it to the other. That'd be way too big. So what really is, I'm not making this up, a good model is a pool ball. In fact, and this is true. This doesn't sound like it's a true thing, but the Earth is rounder and smoother than this is. This has inconsistencies from when it was made. I don't know how they make these things in a mold or something. Um, any little bump on here or scratches on here, which I can see because I've had this thing for years, if you were to blow this up to the size of the Earth, those scratches would be way deeper than the Grand Canyon. So the Earth is actually rounder and smoother than this is. For all of its bumps, for all of its pits, Mariana Trench, all these mountain ranges, all of that, given the size of the planet, it's actually very smooth. So a pool ball, as in billiards, not as in like a beach ball. Um, if you were to put a scratch in the globe, so this is just doing it. Like if this thing had a scratch, 0.1 centimeters deep, it's one more of these equations, which would be x over 12,756 equals the 0.1 for the scratch on the 15.5 centimeter globe. And again, I'll just do that for you. My calculator wants to wake up. 12,756 times 0.1 divided by 15.5. 82.3. So a little tiny scratch would end up being 82.3 kilometers deep. You compare that to the depth of the Grand Canyon, which is 1.8 kilometers deep. Then I'm going to leave this one to you. So I did almost the whole lab for you. Using what you learned in this lab, describe the general shape, the roundness and smoothness of the Earth. Keeping in mind what I just said. This is more rough and less round than the actual planet is, mathematically. We want to see data from your lab in this answer. So basically, when I've graded this in past years, I look to this first, and if I don't see any numbers, it's coming back incomplete. Okay? So go find some numbers that would explain somehow in your head, how can you make sense out of the Earth being rounder and smoother than this pool ball? How do any numbers in this lab support that claim? Which they do. You just got to figure out how to word it. All right. Sound good? Thanks for sticking with me. Another lab down. Take care.